All right, this is the start of a lovely new short chapter. Short, like Mr. Allen. We've got 3 sections, and we're going to be going into 3-dimensional type geometry, all right? So we're going to be getting into planes, which we haven't seen yet. It's going to be awesome. We'll go over naming them and all sorts of wonderful, great things. A lot of vocab in this particular lesson. So a plane is basically just like a surface. Basically what we've been dealing with here in geometry is just a single plane. We've been drawing everything on a plane. You almost think of it as like your sheet of paper. Okay, so it's a flat surface that, you got like points and lines on there. All right, but you can also have lines that are going through that plane. Like here you see that little line MT or line J, depending on how you want to name that one. So this guy right here, that's going through the plane. All right, but points R, P, Q, N, G, or sorry, not G, that's not a point, that's a line, T, those are all points that are on that plane, which are called coplanar. Those points are all coplanar. So let's get into naming a plane. This is the same diagram we had in the last slide there. So in this case, we could call this plane S, all right, with a cursive letter written in uppercase, okay? So this can be plane S. You could also use 3 non-collinear points. So you could call this plane PTR, plane PTR. You could not call it plane PTN because those 3 points are collinear. They lie on the same plane. Okay, we could also call it QTN or QTP. A lot of different names that we could call it here. All right? But yeah, they can't be collinear because that does not actually determine a plane. Imagine, like a tripod for a camera. Think about a tripod for a camera. It's got like 3 legs, right? And it just sits on the ground at these 3 particular points, right? And they're spaced out so that it doesn't topple over. Think about if that tripod just had like 3 legs that went down like this and they were all in line. That tripod would just be like, it would just fall over. Right? It would not stand straight up unless you perfectly balanced it. But when you got 3 points sitting on the ground, spaced out nicely, it stays up because those 3 points would determine a plane. They're lying on that plane. They'll hold that tripod up. That's one way that I think about it. Anyways, all right? All right, so we have if points or lines are coplanar, then, that should be then. So we're talking about coplanar now, not collinear, but coplanar. So if points or lines are coplanar, then they lie on the same plane. If points were collinear, they lie on the same line. So in this case, they lie on the same plane. Lie on same plane. Okay. Now it says any 3 non-collinear points are coplanar. Let's think about that for a sec. If I take 3 points, I could successfully draw a plane through it, okay, or create a plane with those 3 points. Much like any 2 points, if I have this point and this point, I can draw a line through it, right? Those are collinear points. Any 3 points are not necessarily collinear. They could be, but we don't know for sure. But any 3 non-collinear points, meaning they don't lie on the same line, or they could even lie on the same line, those are guaranteed to be coplanar. All right, what about 4? Could I have 4 non-collinear points? Are those guaranteed to be coplanar? What do you guys think? Well, I like to think about a chair. You ever have a wobbly chair before in your life where you could only successfully get 3 of those legs down on the ground while the other one's sitting up in the air? That is a perfect example as to why any 3 points, any 3 even non-collinear points are coplanar, but 4 not so much, okay? 4 points could be coplanar, but it's not guaranteed to be coplanar. 3 points guaranteed. 4 not so much. 4 or more not so much, all right? So let's see here. Can you name 3 coplanar points? Any of those that are sitting on the plane, P, T, Q, R, and N, those are all coplanar, all right? M is not on that plane, all right? It's drawn to not be on that plane. Cool. Awesome. All righty. So lines have three different relationships to one another. They can be parallel, right, where they don't intersect. They have the same slope if we're graphing them. Intersecting. And then there's skew. So skew is basically where they don't intersect, but they're also not parallel. Okay? There are two lines that are in completely different planes. This is something we haven't really seen before. One way that I could explain it is if you were to have, say, a line drawn on the ceiling, right? If I drew a line on the ceiling, and then and I drew a line on the floor, okay? Ceiling, floor. Those lines that I've drawn on the ceiling and drawn on the floor will never intersect. However, they're also not necessarily parallel to each other if they're not in the same plane. Okay? In order to be parallel, they have to lie in the same plane. So if they're not in the same plane, they can't be parallel. If they're not in the same plane, and obviously they can't intersect, we call them skew. All right? Now, planes only have two relationships. They are either parallel or intersecting. All right? Those are the planes there. Cool? Planes are either parallel or they are intersecting. That's about it. Cool. So we have this dude here, right, planking on the escalator. If I were to draw a line on like the floor here, let's say this were the line that I just drew on the floor. He doesn't intersect that line. He's kind of floating above it. But he's also not necessarily parallel to it, right? He's not parallel to it because he doesn't lie in the same plane. All right? So that would be an example of skew. Cool? Or it could even be like if you see like how we kind of have a line in this floor right here. That isn't going to intersect him, and it's also not in the same plane. He is skewed to that line. Lovely. So we have four different ways to determine a plane, and we're going to have little symbols to do that. So we can have three non-collinear points to determine a plane. We already talked about that, like a tripod sitting on the ground. So we can do 3 points, okay? A line and a point not on the line. So a line and a point that's not on that line. That would also determine a plane. All right, we got two intersecting lines to determine a plane. And then two parallel lines determine a plane. The way I often think about these last two are, have you ever seen like tables with like crisscross legs that sit on the ground, or maybe a table that has two long legs that lay on the ground? Those types of things hold the table up. They determine that plane. Okay. If you have any confusion with these, you will want to swing by in class and ask. It's a little bit tough to demonstrate this via video, just doing the best we can here. Okay. A lot of times it's visual. I'll do some examples with people and stuff like that. Okay. So if you're having a little confusion with this, come on in. And if you want to represent this last one just as like our normal parallel symbol, this would be totally cool as well. I'll probably use that most often since we use that for parallel anyways. So let's think about some little combos here. What is the intersection of a line and a plane? Like if I draw a line going through a plane, what does that create? What is the intersection? If I draw a line through a plane like AE is going through that plane, it intersects at B, so that is really just a point. Okay, B, so a point. And actually, there's a specific name for where a line intersects a plane. It's called the foot. Okay. It says, what is the intersection of two planes? Well, here you see two planes coming together. What is that intersection right there? That is a line. Lovely. I often demonstrate this one in class with where a ceiling meets a wall. You can see a line running right along that ceiling and wall where they intersect each other. That's pretty cool. Aha, here we go. The formal definition of a foot. The point of intersection of a line and a plane is called the foot of the line. So in this case, what would my foot of line J be, or line MT be? It would be T. T would be my foot. Lovely. All right, we got some questions here. Some of the ways that this imported obviously are not the best, so we'll do what we can. All right, use the following figure. Use the figure right up there at the top right to answer the following. We got A, B, and C. Determine which plane. C is this point right here, which I didn't do a very good job at. Let's see if I get. There we go. That's pretty good. All right, C is that point. So what plane does that determine? It is that bluish purpley one, which is N. Let's make a fancy cursive N. That was terrible. Okay, I'm going to try that again. Just make it fancy, okay? Pretend as you write uppercase cursive that you're writing to a king or a queen in medieval times. And then that's how you label a plane, is with fancy, fancy letters, okay? It's fancier the better, really. All right? Then it says that B, D, and E, or B, D, E, and what are coplanar points? B, D, E, and C are coplanar points. All right, next one. AC and BD determine what plane, because we have BD, which is this guy here, and AC, which is this guy here. What plane do they determine? Well, intersecting lines determine a plane. That plane is once again N. So fancy as possible. Make it all curvy and fun. There we go. Fancy N. All right. What is the intersection of plane F and plane N? Plane F and plane N. Well, two planes intersecting forms a line. So we could say line BD. Or if you said BC or CD, all those would work because those are all just different names for the same line. All right. And the last question, we have a question mark there. BD and AC. All right. Well, we'll say that was the intersection of those two. What is the intersection of BD and AC? That would just be point C. Okay? BD and AC, they intersect, and that would be point C, because two lines intersecting just gives us a point. Lovely. All right, what would we do without proofs here, children? A great way to end the lesson. This is the last one. It says, given Q, R, S, and T lie in plane M. That is important. They're coplanar. It says that PQR and PQT, angle PQR and PQT are right angles, and RQ is congruent to QT. Prove angle RPQ and TPQ are congruent. Okay. Give myself a little more room. You'll notice that a lot of these proofs, well, we'll get into some properties about our three-dimensional geometry here. Right now, it's more of like a three-dimensional picture, but we're still going about it in a two-dimensional way through these proofs. We don't have anything new as far as properties go. We've just gone through some definitions. We know what coplanar means. They lie in that plane, right? R, Q, S, and T all lie in plane M. P does not. All right, but I know that angle PQR and PQT are right angles. Yeah, that's a little better. Whatever. All right, and then I've got RQ and QT are congruent, and then that almost looks like an angle there. There we go. And then I want to prove angle RPQ, I'm going to put that in blue. RPQ, I want to prove that is congruent to that. TPQ. All right, so it almost looks like I'm going to need to get some triangles congruent here and CPCTC my way out of it. I'm going to take this into a two-dimensional picture here real quick. Essentially what we're dealing with is almost like this type of situation. We got a right angle. We've got congruent, right? This is R, this is Q, P, and T. Now, this is not like an isosceles triangle type of deal, okay? This is not a flat triangle that we're dealing with because really it's kind of bent, right? It's like I folded this triangle slightly and stood it up because this goes here and then it angles, right? That is not straight across, okay? So this is not a straight across thing. It's as if I took this triangle, folded it down here, and then propped it up on a table. That's what's really going on. But a lot of the concepts can still apply. Well, could I get these two triangles congruent? I believe I could use a little bit of reflexive property, and I got some side angle, side action going on. And once I've got that, boom, I've got my angles that I wanted congruent for my proof via CPCTC. Let's write it up. So I've got, let's see here. How about, let's label these angle 1 and 2 for my two right angles. So I can say that those are congruent, because if I'm using SAS, I got to say they're congruent. So the right angles, I know they're congruent. Angle 1 congruent to angle 2, and that would be all right angles are congruent. Then I've got PQ congruent to PT, or sorry, PQ congruent to PQ by reflexive. And now I've got my triangles congruent. So triangle RPQ, how about? And then I'll match up with that. Congruent to triangle, well, RPQ matches up with TPQ. And that is by SAS. So I've got my triangles congruent. I had the sides given to me. I proved my right angles congruent. I got my other side via reflexive. Got my triangles congruent, and now I'm ready for some CPCTC action. R, P, Q, congruent to, angle, TPQ, CP, CT, C. Corresponding parts of congruent triangles are congruent. Woo! Yeah! Lovely.